Day 3, Physics and Honors Physics, Scientific Notation, Significant Digits, Order of Magnitude, and Comparing Numbers. So let's start with scientific notation. I did the first one for you. Bottom line is you always want to put the number in such a position such that the decimal number is less than 10. So in this case, the first case, we have 5 point something. The original number was 548,100,000. So we always move the decimal into the position between the first two digits, always maintaining the number of sig figs. So let's do that in conjunction here. This first number has 4 sig figs. The zeros do not count. So I can put that over here, 4 sig figs. I'll go to order of magnitude here in a minute. But I'm going to do all the calculations here into a scientific notation first. So for example, number 2 has 3 sig figs. You don't count the initial zeros. So to put that in scientific notation, it'd be 4.32 times 10 to the negative fourth. Then I'll do all of them. Here we go. I get the right pen for myself here. So 4.32 times 10 to the negative fourth centimeters. 7.7. 0. This is a lot of sig figs here because all those zeros count plus the final numbers 4, 3, 2, 2 times 10 to the first centimeters. I'm a little bit out of room. 10 to the first centimeters. And then the next one, those 6 sig figs, because you wouldn't put 0.0 unless the 0.0 at the end is significant. So this is 6.87650. The 0 counts as a sig fig, times 10 to the fourth meters. I'll keep going here. 2.8200 times 10 to the negative third inches. So this is all, whoops, that's inches. And then the next one is already in standard form, but once again, all those zeros count because you wouldn't put those last 3 zeros unless they were significant. So you could put it like this. You could leave the number just as is, but I'll do this, 4.007000 times 10 to the 0th power, grams, little g is grams. 10 to the 0th power is 1. You wouldn't need to write that there. And finally, 8.8088, that's 5 sig figs, times 10 to the negative second kilometers. So just to recap then, the second one has 3 sig figs. This third one has 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs. And then 5 sig figs. 5 again. 7. And then 5, if I counted right. So now, order of magnitude. Basically, order of magnitude is an estimating technique used to help us compare numbers, especially numbers that are vastly different than one another that you'll see here in a few minutes. But basically what you do is you look at the number in scientific notation. Up here, let's do number 1. So it's 5.481 times 10 to the 8th. You just look at the first number. Don't do any rounding or anything. If this number right here that I'm pointing at is a 5 or through 9, 5 or greater, okay, you take this value over here for the power of 10 and add 1. So the order of magnitude, or we just say magnitude of that number, is 10 to the 9th meters. 10 to the 9th meters. Number 2, since the first number in that scientific notation is a 4, 4.32, but since there's a 4 there, this number right here is a 4, this is the magnitude, 10 to the negative fourth centimeters. Just write that down. So any number that's a 4 or less, you already have your magnitude right there. You just write that down, just like it is. So, excuse me, number 2, the magnitude is 10 to the negative fourth centimeters. The third one is, since it says 7.7, but the important number is just the very first 7. It's 5 or bigger, so you add 1 to the 10 to the first, so it makes it 10 to the second. The order of magnitude is 10 to the second, which would be 100 centimeters. Number 4 is a 6.8, so it's a 6 bigger than 5. You add 1, 10 to the fourth, you add 1 to that, you make it 10 to the fifth That's the magnitude, order of magnitude. Number 5, 2.8. The 2 is less than 5, so the order of magnitude is already there. 10 to the negative third inches. Number 6, it's a 4. It's less than a 5, so the order of magnitude is 10 to the 0, or just 1 gram. And the last one, 8.8. This is the trickiest one of all. Once again, it's bigger than a 5, or a 5 or bigger. So you take the 10 to the second here, this right here, and you got to add 1 to it. But when you add 1 to that, it's 10 to the negative first, not 10 to the negative third. That'd be subtracting 1. So the answer for number 7, the magnitude is 10 to the negative first kilometers. All right, so comparing numbers, there's 3 basic ways to compare numbers. You can compare numbers by their absolute difference. That's the easiest way. You just subtract them. For example, in the first case, the final number is bigger than the first number. You just subtract them. You just take 15.8 meters, make sure they're both the same units, 15.8 minus 12.3 meters, and we say the final result, the final number is what, 3.5 meters greater? So 3.5 meter increase. Okay, or you would just say the second number is 3.5 meters bigger than the first number. The first number is 3.5 meters smaller than the second number. I'll do part B as well. Same thing for the prom dress. What's the discount? Well, you take the final number minus the initial number. It'll be negative in this case. So I'm going to take the absolute value for now and explain that in words. For example, if I take the bigger number, the $6.55, which is the initial price, minus the final price, I know what the discount was. It's what, $204? So let me erase that. Okay, $204. It was a $204 discount. In other words, the final price is $204 less than the initial price. If you would have taken the final number, 451 minus 655, obviously you would have got a negative 204, which means that's what the discount, the decrease in price is. Most of the time in labs, you'll be doing percent difference. And the equation's up here at the top. I'll use a different color, blue. That is an equation that you're going to want to use most of the year in the labs when we ask you to give percent difference. I don't like to call it percent error. That assumes that you're making mistakes, which we sometimes make, but not always. Just basically, what's the percent difference between your value and somebody else's value or some published value? The essential idea here is you take your final number, your ending number, your measured number, minus the original or published number, divided by the original. In the case A here, the original number was 12.3, the final number is 15.8, so the percent difference would be the 15.8, the final number, so I take the final number minus the initial number, 12.3, and it's the absolute value of that. Well, it's going to be positive anyway, so it doesn't matter. So there's brackets in that equation above there in that blue circle, or that blue oval, divided by the original number, 12.3. So you end up with what? 3.5 divided by 12.3. Oh, and you got to multiply by 100 to get the percents, because if you just do the division, you get the decimal number. So you have 3.5 divided by 12.3, which comes out to be 0.285. And I'll just put it right into percent form. It's 28.5% larger. The final number is 28.5% larger, or increase. So if it's a stock price, that would be your increase in stock price. If the stock price fell from 15.8 to 12.3, you do it the other way around. You do 12.3 minus 15.8 divided by the 15.8, which would be a different answer. You can check that out. So you're always dividing by your original or comparison number or the published number when we're doing labs. Let's do the dress problem. For example, here's a case where it fell. The final number is 451, so you take 451 minus the initial number, 655. Once again, that'll be a negative number, but in percent difference, we're going to take the absolute value. So I'm putting the absolute value bracket around that, divided by the original number, in this case, is 451. So always dividing by the original price, or the comparison price. And in this case, it's a 31 and times 100%. So it comes out to be 0.311 which when you multiply by 100 is 31.1% discount for the dress. Okay, so in the final case here, so 3 ways to compare numbers: by their absolute difference, is subtracting them; their percent difference, which is what you'll be doing most of the time, take the final minus the initial, divided by the initial or original, times 100. But if the numbers are really, really far apart, like these last 2 examples, where you have 2 numbers, one that's huge and one that's small, the huge number here in the last case is 5.72 times 10 to the 9th. Essentially what you do is just take the big number divided by the small number, because it makes no sense to compare these by percent, because the percent difference between these two is huge. The absolute difference is huge. But how many times bigger? How many factors of 10? What's the order of magnitude bigger the 5.72 is times 10 to the 9th? So basically you just take that number divided by the smaller number, 3.66, times 10 to the 4th. In this case, you get 1.6 times 10 to the 5th. So the big number is 1.6 times 10 to the 5th times greater. Or it's, if you wanted to say it a different way, you could say it's 10 to the 5th. It has a magnitude of 10 to the 5th times bigger. You can include the 1.6 times 10 to the 5th. But the main thing is 10 to the 5th is 100,000 times, over 100,000 times bigger than the small number. It's very big compared to the small number. Same thing in part B here. Take the big number. In this case, the big number is the 1.72 times 10 to the negative 14th. That's a bigger number than 2.12 times 10 to the negative 29th. That's a really, really small number. It's a negative 29. You divide those 2 numbers, and you get 8.1 times 10 to the 14th. 8.1 times 10 to the 14th. That's how much bigger the bigger number is. That much bigger, that many times bigger. You could say it has an order of magnitude of 10 to the 15th. That's the order of magnitude of that number that I'm circling right now because of that 8 right there. You up it by 1. So the bigger number has an order of magnitude of 10 to the 15th times more than the smaller number for that particular comparison.